In this module, we will discuss the methods of detecting heteroscedasticity. An important assumption of fitting linear model is that the error variances are same. But when this assumption is violated, we say that the errors are heteroscedastic. When the errors are heteroscedastic, it affects the estimates of the regression parameters involved in the model. In this module, we will look at different methods of detecting heteroscedasticity so that it can be removed before the model is fit, so that the estimates of the regression parameters and their related inferences are not affected. In this current module, we will discuss methods of detection of heteroscedasticity. What do we mean by heteroscedasticity? One of the many assumptions of linear regression model is that the error variances have to be constant. Hence, in a linear regression model, we assume the error term has a normal distribution with mean 0 and variance sigma square. That is, in a model, if we denote the error term by ui, we assume that variances of ui equals sigma square for all I. This is called homoscedasticity. However, when the error term does not have constant variance, that is, variance of error term ui equals sigma I square for each I, we call it heteroscedastic. When can heteroscedasticity occur? Let me explain the occurrence of heteroscedasticity with an example. Consider a regression model in which age is the independent variable or the explanatory variable and annual income is the dependent variable. It is common for teenagers to earn close to the minimum wage, so there isn't a lot of variability in income during the teen years. However, as teens age into their 20s or 30s, some will tend to shoot up the tax bracket while the others will increase more gradually or perhaps not at all. Now, due to this variation in income, the variances of the error terms will also increase with the increase in the value of explanatory variable age, thus increasing the variability in income as age increases and causes heteroscedasticity. Let me present 3 more examples of regression models where heteroscedasticity is present. Suppose in our model, consumption expenditure is denoted by CI and is considered the dependent variable, and income denoted by YI is the independent variable. In this model, the variances of the error term UI increases as YI's increase. In the second example, we have the independent variable DI, which denotes the difficulty of a test, and the dependent variable MI denotes marks obtained on the test. Then in this regression model, variances of the error term UI increases as DI's increase. Lastly, variance of error term UI decreases in certain cases, which is also evidence of heteroscedasticity. Suppose our regression model has an independent variable EI, where EI denotes the efficiency of a person, and the dependent variable is denoted by OI, where OI is the output of a firm. In this model, the variances of the error term UI decreases as efficiency of the personnel increases. When there is presence of heteroscedasticity in a model, we would definitely like to detect it before we fit the model with the data. Here are a few points that we have to keep in mind while detecting heteroscedasticity in a dataset. A detection of heteroscedasticity is only possible after the model has been fitted and the error terms have been obtained. Once the error terms have been obtained, heteroscedasticity can be tested by plotting the residuals against the covariates or the explanatory variables. Apart from the above methods, there are several quantitative tests that one can apply to detect heteroscedasticity. In the following slides, we have discussed several such quantitative methods in detail. In detection of heteroscedasticity, there are several methods. They can be classified broadly into two types. Informal methods. The two types of informal methods are nature of the problem. Knowing the nature of the problem helps in detecting the presence of heteroscedasticity. And we have the graphical method. Under formal methods of detection of heteroscedasticity, we have a number of quantitative methods, some of which are Park test, Glaser test, Spearman's rank correlation test, Goldfeld-Quandt test, Breusch-Pagan-Godfrey test, and White's general heteroscedasticity test. Now let us discuss the informal methods of detecting heteroscedasticity in detail. The first informal method that we use is to know the nature of the problem that we are looking at. Oftentimes, the nature of the problem under consideration suggests whether heteroscedasticity is likely to be encountered or not. For instance, in the consumption expenditure and income study, it was found that the residual variance or the variances of the error terms around the regression of consumption on income increased with the increase in income. Hence, one now generally assumes that in similar studies, one can expect unequal variances among the error terms. Actually, in cross-sectional data involving heterogeneous units, heteroscedasticity may be the rule rather than the exception. For instance, in the consumption expenditure and income data, we had different individuals with different incomes and they can be each considered as a heterogeneous unit. The second informal method of detecting heteroscedasticity is graphical method. Let me point out here that although we call the graphical method an informal method, most of the time it is quite effective in showing the presence of heteroscedasticity in the data. Now, in case of graphical method, if there is prior information about the nature of heteroscedasticity, then one can do the regression analysis based on the assumption that there is no heteroscedasticity present. We then obtain the residuals after fitting the regression model and perform a post-mortem analysis of the square of the residuals. The squared residuals, ui squares, are plotted against yi hat, which are the estimated values of our dependent variable yi from the regression line. Our idea here is to find out whether the estimated mean value of y is systematically related to the squared residuals. For example, let us take a look at the following plot. We have plotted the square of the residuals against our covariates, and it reveals that there is no systematic pattern between the two covariables, suggesting that no heteroscedasticity is present. However, let us consider the example of age and income, where income is the response and age is the explanatory variable. When we plot the square of the residuals, it shows a cone-like pattern, which means as the value of age increases, the variances or the square of the residuals increase. Thus, there seems to be a systematic pattern in the variances. This is evidence of the presence of heteroscedasticity. Let us here discuss some of the formal methods or quantitative methods of detecting heteroscedasticity. The first method that we will discuss here is the Park test. Park test formalizes the graphical method. That is, it mathematically explains the relationship between sigma I square and the explanatory variables, where sigma I square is the heteroscedastic variance of the error term. The functional form suggested by Park is of the form sigma I square equals sigma square times xi raised to the power beta times e raised to the power of vi. Or, taking the log on both sides, the model can be rewritten as log sigma I square equals log sigma square plus beta log xi plus vi, where vi is the stochastic disturbance term and xi is the explanatory variable, and sigma I square is the heteroscedastic variance of the error term. Since sigma I square is usually not known, it is estimated by hat ui square, and the following regression is run. Using the model, log ui square hat equals log sigma square plus beta log xi plus vi, where hat ui square is the estimated square of residuals obtained after fitting the regression model ignoring heteroscedasticity. In this model, we can write log sigma square denoted by alpha plus beta log xi plus vi, and this model is of the same form as a simple linear regression model, where alpha equals log sigma square, which is a constant term. If the coefficient beta in the above regression model turns out to be statistically significant, then that suggests presence of heteroscedasticity. In other words, the null hypothesis for testing heteroscedasticity is H naught such that beta equals 0. And if it turns out to be insignificant, we accept the assumption of heteroscedasticity. Hence, the Park test is basically a two-stage procedure. In the first stage, we run an ordinary least square regression ignoring the fact that heteroscedasticity is present. We then obtain hat ui, where hat ui denotes the estimates of the residuals from this regression, and then in the second stage, we fit the above regression model using log of hat ui square as the dependent variable and the covariate xi. Although the simplicity of the Park test is quite appealing, Goldfeld and Quandt have argued that the error term vi introduced in the regression model between the residuals and explanatory variable may not satisfy the ordinary least square assumptions of homoscedasticity. And hence, we will look at the second formal method of detection of heteroscedasticity. The second method that we will use here is the Glaser test. The underlying idea behind Glaser test is the same as that of Park test. However, after we obtain the residuals ui hat from the regression model in the first stage, Glaser suggested the use of the absolute value of the estimated residuals instead of the square of the estimated residuals ui hat and regress it on the explanatory variable x. In his experiments, Glaser used either one of the following functions. The following functions are modulus of ui equals beta 1 plus beta 2 xi plus vi, mod of ui equals beta 1 plus beta 2 square root of xi plus vi, where we use the square root of the explanatory variable, or modulus of ui equals beta 1 plus beta 2 1 over xi plus vi, where we regress the absolute value of the error terms on reciprocal of the explanatory variables xi. Or we can use the model where we regress modulus of ui on the square root of beta 1 plus beta 2 xi plus vi. In other words, we regress the modulus of ui on the square of the linear regression model beta 1 plus beta 2 xi. Or finally, we can use another model which is of the form modulus of ui equals square root of beta 1 plus beta 2 xi square plus vi, where vi in each of the above model is the error term. Now, in case of testing homoscedasticity, we wish to test the null hypothesis such that beta 2 equals 0 against the alternative hypothesis beta 2 not equals 0. In this test again, Goldfeld and Quandt pointed out that the expected value of the error term ui is non-zero and the term itself could be suffering from heteroscedasticity. An additional problem of the Glaser test is that the last two models, such that modulus of ui equals square root of beta 1 plus beta 2 xi plus vi, and modulus of ui equals square root of beta 1 plus beta 2 xi square plus vi, are nonlinear and hence cannot be estimated using the usual ordinary least square procedure. Glaser noticed that in case of large sample sizes, we can use any one of the first four regression models suggested by him. However, in case of small samples, they may be used as a first stage device to learn about the presence of heteroscedasticity, which may then be detected using more elegant methods. The third method of detecting heteroscedasticity is the use of Spearman's rank correlation test. We know that Spearman's rank correlation coefficient is defined by 1 minus 6 times sum over di square divided by n times n square minus 1, where di is the difference in the ranks assigned to two different characteristics of the ith individual, and n is the number of individuals in the sample. This rank correlation coefficient can be used as a tool for detection of heteroscedasticity as follows. We first fit a regression to the data of y on x as yi equals beta naught plus beta 1 xi plus ui, and we obtain the estimates of the residual ui denoted by ui hat. Taking the absolute values of the ui's hats, both ui hat and xi are ranked either in ascending or descending order, and the Spearman correlation coefficient is then computed using the formula on the previous slide. The significance of the correlation coefficient can then be tested using the following t-test statistic, where t equals Spearman rank correlation coefficient r times square root n minus 2 divided by square root of 1 minus Spearman rank correlation coefficient square. This t statistic follows a t distribution with n minus 2 degrees of freedom. If the t value exceeds the critical value, we accept the null hypothesis that Spearman rank correlation coefficient equals 0, which indicates heteroscedasticity. If the regression model involves multiple regression equations, then RR, or the Spearman rank correlation coefficient, is computed and tested for each of the x variables separately. Now let us illustrate the rank correlation coefficient test using an example. To illustrate the rank correlation test, we consider the data pertaining to average annual return and the annual return. The regression model is fitted and the residuals are obtained for computation of Spearman's rank correlation coefficient denoted by R, which is given by 1 minus 6 times sum over di square divided by n times n square minus 1. The null hypothesis about heteroscedasticity is then tested using the t statistic using the formula Spearman rank correlation coefficient RR times square root of n minus 2 divided by square root of 1 minus RR square. For the computation of rank correlation test, we have used the following data set. The data set contains the names of different mutual funds, their corresponding average annual income denoted by yi, which is the dependent variable, and corresponding to each of these mutual funds, we have the x variable or the independent variable, which is denoted by xi, and xi is the annual return. For each of these mutual funds, we fit a regression model of yi over xi, and from the regression model, we obtain the estimates of yi's, or the estimates of average annual income denoted by yi hat, and we obtain the estimates of the square of residuals denoted by ui square hat. We rank the ui square hats and we rank the corresponding xi's in decreasing order. We then obtain the differences denoted by di and obtain the square of the differences because we needed to compute Spearman rank correlation coefficient using the formula in the previous slide. Now, after we use the formula, we compute Spearman rank correlation coefficient and it turns out to be 0.3333. And using the formula for obtaining the t-test statistic, we obtain the value of the test statistic as 0.9998. For 8 degrees of freedom, the t-test statistic value is not significant at 5% level of significance. Thus, we fail to reject the null hypothesis. Hence, there is no evidence of heteroscedasticity present. Moving on to the next formal method of detecting heteroscedasticity, we will discuss the Goldfeld-Quandt test. The Goldfeld-Quandt test is one of the more popular methods of detecting heteroscedasticity. This method is applicable when one assumes that the heteroscedastic variance sigma I square increases with the increase in explanatory variable. In other words, we only use this test to detect heteroscedasticity if we have reasons to believe that the heteroscedastic variance has a positive correlation with the explanatory variable. That is, sigma I square increases as xi increases. Let me walk you through the steps involved in performing Goldfeld-Quandt test. In the first step, we arrange the observations in increasing order of xi's or in increasing order of the explanatory variables. In the second step, we delete C central observations so that there are now two sets of n minus C over 2 observations each. In step 3, we fit two separate regression models to the two sets of data and calculate the corresponding residual sum of squares, denoted by RSS1 for the first dataset and RSS2 for the second. In the fourth step, we calculate the F-test statistic, which is given by the residual sum of square for the second model over the residual sum of square for the first model. This F statistic follows an F distribution with degrees of freedom n minus C divided by 2 minus P and n minus C divided by 2 minus P. If this F statistic is large enough, we reject the null hypothesis of heteroscedasticity. That is, if F statistic is greater than F n minus C over 2 minus P and n minus C divided by 2 minus P, comma alpha, where alpha is the fixed level of significance. Now, in performing the Goldfeld-Quandt test, we first need to fix the value of C, where C is the number of observations that we delete from the center of our arranged dataset. Now, for choice of C, if we choose C to be very large, it means that more discrimination among the variances in the two groups of dataset is possible. But C being large also means less degrees of freedom for the two remaining sets of data that we use to perform the test and hence less efficient estimates of the parameters. Now, C central values that are omitted such that we can sharpen the difference between the low variance and the high variance groups. It may also be noted that in case there are more than one explanatory variable, we can rank the observations according to any one of the x variables and then delete C central observations and carry out the remaining steps of Goldfeld-Quandt test as before. Now illustrating the Goldfeld-Quandt test using consumption expenditure and income dataset. The following is the data on consumption expenditure and income. The data contains n equals 30 observations which are presented in the following table. Now after the observations are arranged in increasing order of xi's, it looks like the data set given in the following table. After we have arranged the data set in increasing order of xi's, we delete C equals 4 central observations so that we now have two sets of n minus C over 2, which means 30 minus 4 over 2 equals 13 observations in each of the two data sets. Now regression models are fitted to the first and the second set of data, and we obtain the corresponding residual sum of squares for each model. After we fit the regression model to the first set of data, the regression model that we obtained written in terms of the estimated parameters is yi hat equals 3.4094 plus 0.6968 xi with residual sum of square RSS1 equals 377.17 and degrees of freedom 11. And after we fit a regression model to the second set of data, the regression model that we obtain is yi hat equals minus 28.0272 plus 0.7941 xi with residual sum of square RSS2 equals 1536.8 and degrees of freedom is 11. Now from the two residual sum of squares, we obtain the value of the F test statistic, which is given by the residual sum of square of second model divided by degrees of freedom over residual sum of square of the first model divided by degrees of freedom, which equals 1536.8 divided by 11 over 377.17 divided by 11. And the resultant value of the test statistic is 4.07. The critical F value for 11 degrees of freedom of numerator and 11 degrees of freedom of denominator at the 5% level of significance is 2.82. Since the estimated F value exceeds the critical value, we may conclude that the null hypothesis is rejected, that is, there is heteroscedasticity in the error variance. Moving on to the Breusch-Pagan-Godfrey test for detecting heteroscedasticity. In case of Goldfeld-Quandt test, the selection of the optimum value of C is necessary. Also, the method depends on identification of the x variable with which to order the observation. Also, in case of Goldfeld-Quandt test, we can perform the test only if the residuals are positively correlated with the explanatory variable x. We can overcome the limitations of Goldfeld-Quandt test by using the Breusch-Pagan-Godfrey test. To illustrate this test, assume a k-variable regression model, where the model is written as yi equals beta naught plus beta 1 x1i plus beta k xki plus ui, where ui is the error term and x1i, x2i, xki are the k explanatory variables. We assume that the heteroscedastic variance sigma I square is some function of the variables xi's as follows, and the model is written as sigma I square equals alpha naught plus alpha 1 x1I plus alpha k xki, and we run the regression model. And the test of heteroscedasticity can simply be written in terms of the null hypothesis, which is H naught such that alpha 1 equals alpha 2 equals alpha m equals 0. And if we reject this null hypothesis, then that is evidence of the presence of heteroscedasticity in the model. Finally, let me discuss White's general test of heteroscedasticity, which will be the last formal test of heteroscedasticity that we will discuss in this module. Let us first write a model in terms of the dependent variable yi and two independent variables x2i and x3i. The model for the ith individual is written as yi equals beta 1 plus beta 2 x2i plus beta 3 x3i plus ui, where ui is the error term. For a given data, we estimate the parameters and the ordinary least square residual ui hat from the above regression model. After we obtain ui hat, we run the auxiliary regression model of the square of estimated residuals ui hat on our explanatory variables. The model can be written as ui hat square equals alpha 1 plus alpha 2 x2i plus alpha 3 x3i plus vi. Now, the R square or the multiple correlation coefficient square of the above model is computed under the null hypothesis that there is no heteroscedasticity. N times R square follows a chi-square distribution with degrees of freedom equal to the number of parameters in the auxiliary regression without intercept, where n is the sample size. To test heteroscedasticity, our null hypothesis here is R square equals 0. So if we reject the null hypothesis, then we have evidence that there is presence of heteroscedasticity. Now, if there is heteroscedasticity present in the dataset, there are a few consequences. The estimate of the regression parameter are still unbiased in the presence of heteroscedasticity, but they are inefficient. The variance of the estimates are too large, hence we cannot apply the formula of the variance of coefficient to conduct the test of significance and to construct confidence interval. The prediction of dependent variable yi for a given value of x based on the estimate of beta hat obtained from the original data could have high variance, that is, the prediction would be inefficient. In the presence of heteroscedasticity, the generalized least square estimates of the parameter beta is more efficient than the ordinary least square estimate. That is, the variance of beta hat obtained under generalized least square is less than the variance of estimate of beta under ordinary least square estimates. Heteroscedasticity does not affect the unbiasedness of ordinary least square estimates of beta, but it is no longer the best linear unbiased estimate, or in other words, the variance of the OLS estimate of beta is no longer the lowest variance. We will take another module to discuss the differences of a generalized least square estimate method and the ordinary least square estimates technique when heteroscedasticity is present in our dataset. In this module, we have discussed in detail the methods of detecting heteroscedasticity. When heteroscedasticity is present in dataset, then ignoring heteroscedasticity and fitting a model would result in regression parameter estimates which are faulty, and also we will get the estimates of their standard errors which are not true. So, the inferences that we draw about the regression parameters based on these numbers will also be affected by the presence of heteroscedasticity. So, it is very important that heteroscedasticity is first detected and removed before a model is fit. In this module, we have discussed 6 different methods of detecting heteroscedasticity, and each of them have been illustrated using a data set, and we have also illustrated how we can use R in order to detect heteroscedasticity in a data set.